Assalamualaikum and a very good day to Doctor. Today we would like to present regards to the project. So I will first introduce our group member. Number one is me myself, Nurazlina binti Sulaiman. Next, Muhammad Isma Salihin bin Matsani. And lastly, Ahmad Imran Zakwan bin Khazilam. I will begin our presentation with the introduction. So, what is the meaning of system power cycle? Basically, we also call it as system power plant, which is the working fluid changes from liquid to vapor and then back to the liquid state. This succession of processes is called the vapor cycle. We consider vapor power cycle in which the working fluid is alternatively vaporized and condensed. We also consider power generation coupled with process heating called cogeneration, and it is an energy system that can create two valuable commodities at the same time. It includes combine of heat and power plants, which create both electricity and usable heat from a single plant. When compared to traditional power and heat delivery, cogeneration is a highly efficient energy direction that produces primary energy savings. The continued quest for higher thermal efficiencies has resulted in some innovative modifications to the basic vapor power cycle. Among these, we can discuss the reheat and regeneration cycles as well as the combined gas vapor power cycle. Steam is the common working fluid used in vapor power cycle because of its many desirable characteristics such as low cost, availability, and high enthalpy vaporization. Therefore, steam power plants commonly referred to as coal plants, nuclear plants, or natural gas plants depends on the type of fuel used to supply heat to the steam. However, the steam goes through the same basic cycle in all of them, and eventually all can be analyzed in the same manner. So here is the pros and cons of the steam power cycle. For the positive way, we can say it's easily be integrated with other power generation technologies. A well-established technology can use a variety of heat sources, can also be installed anywhere near fuel and water supply. But there are also some of the negative side, which is produces large amount of waste heat, has a low thermal efficiencies, requires a large amount of water for cooling, and also air pollution from smoke farms.
Hello, Assalamualaikum. I'm Muhammad Ismail Salim bin Matsani, MA21053. I will make a presentation to explain about one of our cycle that we use to achieve our objective, which is to find the maximum of thermal efficiency 40%, which is the cycle that we use is simple ideal Rankine cycle. By the end of my presentation, we will know which is this cycle is achieve the objective or not. So before we go to the calculation, I will briefly explain about ideal Rankine cycle. The four components of the ideal Rankine cycle, which is a pump, a boiler, a turbine, and a condenser, all run in a steady flow regime. When compared to the work and heat transmission, the kinetic and potential energy change of the steam are so minor that they are disregarded. Since no entropy is produced due to isentropic nature of the pump and turbine, the amount of work produced is maximized. There is no work involved with the boiler or the condenser. The ideal cycle for vapor power plants is the Rankine cycle, which is why we try to do this cycle. The simple ideal Rankine cycle does not involve any internal irreversibility and consists of the following four processes. There are two diagrams that we use, which is TS diagram and system figures diagram, to make us more easily understand about the process that have been going on in this cycle. So from 3 to 4, the process is isentropic compression in a pump. Then after that, from 4 to 1 process, it became constant pressure heat addition in the boiler. Then after 4 to 1, we go to 1 to 2 process, which is isentropic expansion in a turbine. Then lastly, from 2 to 3, the process that happened in the cycle is constant pressure heat rejection in a condenser. Then we go to our calculation. We assume that steam enters the turbine at 16 megapascal at 560 degrees Celsius. Then we put P1 equal to P4 in terms of the pressure value. Then we assume also that the condenser pressure is 8 kilopascal. and P2 is equal to P at 3. Then the efficiency of turbine is 0.83 and condenser is 0.65 according to the question given. First, we find the value for H and S at 16 megapascal, 560 degrees Celsius. We find the value in the saturated water table. Then, at 8 kilopascal, we find the value for X to S using the formula S1 equal to SF plus X to S times SFG. As usual, the value we get is from the table at 8 kilopascal pressure. Then we go to the state 2 enthalpy state, which is H to S. We find our H to S value using the formula HF plus X to S times HFG. After that, by using turbine efficiency formula, which is H1 minus H2 divided by H1 minus H2S, we get the value for H2. Then at state 3, at 8 kilopascal, we find value for H and V value at the table. Then we use the value put in the work pump ideal formula to get the WP value. And after we get the WP value, we count our WP actual value by divided our WP value that we get just now with turbine efficiency, which is 0.83. Then we find our H4 value using formula H3 plus WP actual. Then for the W net, we use the formula mass flow rate times by H1 minus H2 minus H4 minus H3. The mass flow rate value, we assume that the mass flow rate value that we use is 120 kg per second. Then after we get our W net value, we find our pressure in using the formula mass flow rate times H1 minus H4. Then we just put our H1 and H4 value, put in the formula, and we get the pressure in value. Then lastly, to find our thermal efficiency, we use formula W net divided by pressure in. Then so the thermal efficiency value that we get is 35%. Then we are not achieve our objective, which is to get a minimum of 40% in thermal efficiency. So to achieve our objective, we use another cycle process to get the minimum of 40% thermal efficiency that will explain by my friends.
Okay, we continue the reheat Rankine cycle. Okay, first we achieve most two issue. In turbine is a two-stage turbine. It is the high pressure test and the lower pressure test. Okay, with a reheat in between, we is frequently utilized in genuine steam power plant. Okay, the second, the steam is warm at constant pressure to the first intake temperature in the boiler during the first stage. It is the high pressure stage, which is expand isotropically to an intermediate pressure. Okay, the third is the steam has spanned isometrically to the considered pressure during the second stage. It is the lower pressure test. Okay, so we can see the TS diagram for the reheat Rankine cycle, and the D diagram with using the two type of turbine. It is the high pressure test and the lower pressure test. Okay, we continue for the example of Rankine heat cycle. Okay, as we know, we have the efficiency of turbine is 85% and the efficiency of the compressor is 65%. So how we must use to get the efficiency at least 40%? Okay, first we assume the T1 is 20 Celsius and T3 is 700 Celsius. So for the CP is 1.005 and CV is 0.718. But for the K, we assume the 1.4 and the R is a 2. Okay, for the first step, we continue at the point 1. Okay, point 1, we need to find H1 and V1. Okay, first, we know, we assume the T1 is 220 Celsius and the P1, we assume the 5.0 kilopascal. Okay, for the table E5, we can get the H1 and the V1. Okay, for H1 is HF, we get 137.75, and the V1 is a VF, we get the 0.001005. Okay, we continue at the point 2. Okay, point 2, we assume the T2 is 10 megapascal. So we using the formula W in equal H2 minus H1 to find the H2S, and we get for the answer for H2S is 147.7950. Okay, after that we find the efficiency of, we using the pump efficiency of 65%, and to find the H2. So H2 we get the 153.2088. Okay, we continue at the point 3. Point 3, we already assume T3 is 700 Celsius and the P3 is 0.2 megapascal. Okay, for the saturated at the 10 megapascal, we get the T is 311 Celsius, and then we get H3 is 3876.1, and S3 is 7.0954 at the point A6. Okay, after that we continue at the point 4. Okay, point 4, as we consider at the point 3 and point 4 have the same S, so S3 and S4 is same. It is 7.0954. Okay, after that we look at the table A5. We find the SD at the 275 kilopascal, and we get the value of SD, SF dan SFG. Okay, after that we're using the formula X4 equal S4 minus SF times to SFG, and we get the X4 is 1.0139. Okay, after that we continue to find the H4S. So we look at the table A5, we get the value of HF dengan HFG, and we put at the formula, and we get the H4S is 2751.0508. Okay, another step we using the turbine efficiency is 85%. Can we find the H4 is 2901.6732. Okay, after we get the formula of the answer, we continue at the point 5 and point 6. Okay, point 5 and point 6, we at the point 5 we just find the H5 dengan S5 at the table A5. Okay, at the point 6 we need to find the value of H6S is 2758.1862. Okay, after and we already take a turbine efficiency to get the H6. Okay, after we get all the value from point 1 to the point 6, okay, we can calculate the Q in, Q out, and the W net. Okay, for the Q in we get the 4753.028, and the Q out we get the 2791.7358. Okay, for the W net, Q in minus Q out. For the examples, we get the 1837.3872. Okay, after that we can find the thermal efficiency, and so we get the 41.26%. So we achieve the question, and at least 40% we must to get. So the final we get 41.26. So it's achieved.
So in conclusion, the project objective was achieved by the end of the project because we had fully utilized the theory that we had learned during the class throughout this semester to complete our project. We had chosen two types of designs for the steam power cycle that achieve a cycle of thermal efficiency at least 40% under the conditions that all turbines have isentropy efficiencies of 83% and all pumps have isentropy efficiency of 65%. Firstly, we choose a simple ideal Rankine cycle, and then we get 35% of thermal efficiency. Next, we tried the reheat Rankine cycle design to see whether it can achieve our condition, and eventually we got at least 41.26% of thermal efficiency, which showed we did achieve all of the conditions are given. Therefore, we could say the Rankine cycle with reheat would be the most efficient option to achieve a cycle of thermal efficiency.